Welcome to the live interactive session for the course Advanced Transition Metal Organometallic Chemistry. So, in this problem solving session series, we have reached to the week 8 content. So, in this course, we have started seeing some ligands, that is different number of carbons ligand, and we have finished our ligand system with carbon number 8, and also uh, we have seen some heterocycles, that is containing nitrogen and oxygen and sulfur. So as a ligand to the metal center. So from this last week we have lift ourselves to the extent of this organometallic chemistry to in the application part, that is mainly in the homogeneous catalysis. So in this catalysis system we have started with palladium catalyst, some cross coupling reactions. So as in the last few session, I will not go through this slide which is already taught in the lecture series, but I will start with the problem first, and then by solving the problem, their solving approach, I will try to discuss the problem problems and the theory and the chemistry behind it. So I will wait for a few minutes, then I will start solving problem from my side. In this problem solving session I will try to uh, keep my camera off when I am sharing the slides, but when again I am talking to in the video mode, I will turn it on. Okay, I will wait for a few minutes for if for the participants, and then I will start solving problems from my side. So welcome again for the problem solving session for the NPTEL course Advanced Transition Metal Organometallic Chemistry. With this problem solving session, we have come to the reach week 8 session. Here in this session, as a team member of this course, I am like the TAs of this course. I am discussing some sample problems which is uh, closely related to the assignment problem but different from them, but these problems will help you to approach the portal problem as well as the problems in the portal in the final examination. So in few series where I have shown that how to approach the problem and how different methods is available to reach the correct answer. Sometimes the option eliminating method is quite helpful to reach out the correct answer. So as I have already stated in the previous series class previous session that I will not discuss the entire course content, but I will go through the problems of this week, and by solving the problem I will discuss the weak content and for better understanding and approach how to the questions to get the correct answer. So with this, without wasting any time, I'll start sharing the this week from this week content with the in the form of question, and I will try to discuss the every question is as much detailed as possible and try to solve it in more easy way to get the correct answer in. Okay, so let's I am sharing my slide, that's why I am turning my video off. Okay, welcome again to this live interactive session of the NPTEL course Advanced Transition Metal Organometallic Chemistry. So in this week 8 content, we have seen some different cross coupling reactions. Like first we started with the alkylation of alkyne, that is the very important reaction we have seen in the first type, is the mainly a CC cross coupling reaction. And then we move to ourselves to the most important two kind of reaction. One is the Heck coupling reaction, another is the Suzuki coupling reaction. And these two reaction is well studied in the last 20 years, and also got the Nobel Prize. So and this reaction is more useful as from laboratory to the industrial synthesis of different important products. So and the last of this week we have seen the another coupling reaction which is a Steely coupling. So without wasting time, we are going to the first question. So here in this catalytic reaction we have seen that we are using the palladium as a metal ion. So palladium has a two major types of oxidation step. One is the palladium 0 and another is the palladium 2. So for why is palladium? Because these two oxidation step for this palladium is quite stable, and the palladium is less toxic than other heavy metals like rhodium and iridium, which is known for their best catalytic effect. And also the palladium is economically favored, that is more cheaper than rhodium and iridium. iridium metal. That's why in this we have used the palladium metal in different, and it goes to the industry scales, industrial large scale synthesis also. So that's why the importance of the palladium is very mm, well discussed here. So with this is the first question of today's discussion series, is that the step A of the following catalytic cycle is A. That is, we have seen the catalytic cycle in previous session, that um, we have already seen our catalytic cycle in previous session. So here we have different process, that is, in a catalytic cycle we are having different process in the cycle. So I will explain the different process with this with this catalytic cycle as an example. So our the our question is the step A, that is this step is what is called it is sigma pi rearrangement, is this oxidative addition, it is nucleophilic attack, or it is the Wecker oxidation. So we can have different step, that is the step A, step B, and step C, and step D. We have 4 steps in our catalytic cycle. So in this catalytic cycle we need to know the every step for this reaction, for palladium catalyzed reaction. So palladium catalyzed reaction, so any step for the first step is this, we need to know it is, that is here palladium L4 is losing 2 is ligand to give the palladium L2. Here the palladium is mainly zero oxidation state. With this zero oxidation state, when this halide, it is the vinyl, or this substrate came, it undergo the oxidative addition from palladium 2 0 to palladium 2. So this is, so as the palladium getting oxidizes from 0 to 2, we are naming this step as, and this also the substrate is adding to the palladium, so we are naming these steps as, we are naming this step as the, we are naming this step as oxidative addition, simply O dot A. So here we have got our answer, that is our first step is the oxidative addition. So here for the question 1 our answer will be the oxidative addition, but we have other step like B, C and D in our reaction. So for this we need to know the every step, the name of the every step, which is very important in our catalytic cycle, or when we are reading the catalytic reactions for palladium. So the next step is, we have seen that here this carbanion X minus is leaves and is with the palladium, and all here the this substrate is binding with the in an anionic fashion. So here next step we have seen that these substrate, it undergo a rearrangement to give the eta 3 bound palladium complex, so which is a reactive intermediate in catalytic cycle. So as these undergo rearrangement, so we call this step, so when the sigma, this is a sigma bond and this is a pi bonding type complex, so we call this step as a sigma 2 pi rearrangement. Sigma 2 pi rearrangement. Next we have seen that there is a nucleophile, it is a nucleophile which undergo the attacking this substrate, which that is the eta 3 substrate, to give our another intermediate. As nucleophile is attacking to this eta 3 bound substrate, we called a nucleophilic attack. That is the option number 3 we have. So this step, option C here, the C step is nucleophilic attack. And here we have the last step, that is the step D, when this nucleophile binding with this substrate to give our product, and the palladium also the X minus the anion is getting back. So here we are going to our, again this is the palladium 2 to palladium 0, that is the reduction again is happening, and we are calling is a reductive. Here palladium is also 2, and the final step it is going to palladium 0. So this is the reductive elimination. So with the product, that is the reduction of the palladium center and elimination of the product, so we called it as a reductive elimination. We call it a reductive elimination. So now we got the name of this our name of the our fourth step in any palladium catalyst cycle. So first, for this kind of catalytic cycle, so first step is oxidative addition. The second step is sigma pi rearrangement, as this sigma bonded ligand is converting to a eta 3 pi bonded in the palladium complex. Then the attacking of the nucleophile, that is basically another substrate which undergo the palladium, then undergo again reduction, keep the palladium 2 to palladium 0 with the elimination of our desired product, which is, so we go, so say as the elimination and reduction happening, we calling as a reductive elimination step. So you got the fourth step with this catalytic cycle. So I think this problem is often, the question is clear. Now I am moving to my next question. My next question is, the product of the following reaction is. This is a very important and interesting example of the another kind of palladium catalyzed reaction. Another example of palladium catalyzed reaction. Another example of palladium catalyzed reaction. So here we have seen that this carbon atom is in the all the product, it should couple with this. So here we are calling this reaction is our another palladium catalyzed coupling reaction, that is the CC coupling reaction. We called it a Hague coupling. We call it a Hague coupling reaction. This coupling reaction is very much important, because the coupling of the here we have seen that this is also sp2 and this is also sp2. So coupling of an sp2 carbon is quite difficult and challenging, with the retention of other functional group, or with the with hampering the other functional group. So here we have seen that this reaction it is happening seamlessly with help of only 1% mole percent of palladium catalyst with the help of PPH3, which forms help to the palladium 0 species. So in this reaction we need to the product, so we will see that here for with the study of this reaction we need to see first the mechanism or catalytic cycle for this reaction. So for this we need to see the mechanism of this reaction. fast. Then I will discuss the product will came automatically. So the Heck reaction, the mechanism is here. We have our palladium acetate. So PD PD acetate is fast undergo, that is the 2L and ET3N. ET3N. Our L is PPH3 and X is halogen. We have seen it undergo PDL2. Now this step undergo the R1X to give the PD X. So I have said this step is oxidative addition. Then we have, and this step is oxidative addition, and we have our this R. This undergo the addition to give PD L X R, that is the insertion of H R dash, that is this group is inserted with this palladium alkyl group. Now next step is going to this the elimination of this product with this the beta hydride elimination to give our desired product. And the palladium here becoming palladium hydride complex H L X. Here the palladium is also in +2 step. Now for active catalyst you need to go to the plus 0 state. Here the role of the ET3N which abstract this hydride to from the ET3N H X. So this is the formation of the hydride. It will take this take this to undergo the reductive elimination of this palladium center to be the active catalyst and the cycle undergo. One step to mention in this cycle that this should not contain any halogen, any beta hydrogen, any alpha hydrogen. So which if it contain hydrogen, then it will undergo the beta hydride elimination to again give this olefin. Okay, so for this we have the vinyl aryl is more suitable for these types of thing. So here we have seen how the Heck coupling is occurring. Heck coupling only limitation is that our substrate should not contain an halogen. That is, for example, if we have this like this, R. So here the hydrogen is there. hydrogen is there. So if we have X over here, so it will have, so this hydrogen will fall and this X can be, so this gives the olefin, this will give the olefin. So this step will not go, that is oxidative addition will not go in the forward direction. So this step will go back to the original palladium catalyst, palladium 0. So the further step, that is the insertion, eliminate, and the elimination will not happen. The beta hydride elimination will not happen in here. This is the main important for our this Heck coupling reaction. So here we have seen that we have here no beta hydrogen, no hydrogen is there in this center, and we have our Br and another our alkene. So this will give the coupling, and this. So another thing we need to see that this Et3N is also in stoichiometric amount, to get this reaction. So here palladium is acting as a catalyst, but here we need to add the Et3N in the stoichiometric amount of the substrate to move forward this reaction. So here our product will be simple C. Here one thing we need to remember, that the cis product for this reaction, we can also have the cis product. This kind of that is this double bond undergo the cis, and also this. So the cis product after obtaining from this reaction is not possible, or it doesn't happen. It always gives the trans selectivity. So this is the another important example of the palladium example of the organometallic reaction. This is the palladium catalyzed sp2 cross coupling reaction. Here with this, I think this question is almost clear, and we have also seen that the mechanism of the reaction. So now we are going to the next question. It is the question number 3. Question number 3 is suggesting that the major product of the following reaction is. Here also the same reaction, that is this is an example of Heck reaction. This is also the example of Heck reaction. So Heck coupling reaction. Here this thing is already added. That means this step is a step after the step A. That is the after the oxidative addition way. Then after this is happened. So DIPP is mainly a chelating kind of ligand. So here the palladium is in +2 state, and here coupling partner is PHX, and this is our another substrate. So we have seen that in solvent, this reaction is solvent dependent, and when we have this THA solvent, we have our solvent with the THF, which is mainly a non-polar solvent. So this THF will, so for this coupling reaction, as we have seen earlier, that the cis and trans both the product will be from. So one product is PH. This one, another product can be, that is the trans couple product pH. So here when we are having our highly polar solvent, when the anion is same, when we are having the highly polar solvent like DMF water, we are getting the cis trans ratio almost 50-50. But when we are using the non-polar solvent, non-polar, like the TMF, like the THF, which is for very less polar solvent, we are having our ratio is selectively towards the trans. So THF is the selective product towards the trans. So our product will be this one, the option C will be our major product. So here, as the solvent is mentioned here, we need to look at the solvent for this kind of reaction. As we know that this Heck coupling reaction is also a solvent dependent reaction. So our product here, as the depends on the solvent polarity, so it will show the our product or of this reaction, or mainly the major product. This word, the major product, as is mentioned, the major product for this reaction will be mainly the, for this reaction our cis percentage will be 8%, whereas the 92% will be our trans product. So the importance of this word major is also important. Okay, so with this I completed the question number 3, which is a very interesting and good question, and very we need to remember many things when we are solving these kinds of question from the catalytic problems. This question is again from the catalytic cycle, and from question in question 1 I have discussed this question very much in detail. So I think I expect that some participant will be there, and I'll ask this question to the participant. So, but as nobody is there, I think nobody is there. Mm, as nobody is there, so that's why I have I have given this question in second times, so that the student can answer from in live session. Okay, as nobody is there, I will answer this question, but this time I will also explain the different stages of this catalytic cycle reaction. So this catalytic cycle reaction is the catalytic cycle for the um, Suzuki coupling reaction. So how you know this is Suzuki? Because Suzuki coupling reaction is mainly occurred by a substrate of boronic acid. So here we have having that boronic acid and a base. Base means another. So this catalytic cycle is mainly a catalytic procedure for the Suzuki coupling reaction. So I will explain this catalytic cycle again, and I will and you see the right answer for the following step A. Here A is the last step of our catalytic cycle. Okay, so coming back to the fourth question, so as we have seen in our substrate is a boronic acid. So in presence of base, it is converting. So this catalytic cycle is uh, mm, galactic cycle for the Suzuki cross coupling reaction. So here we have seen that, like the previous step, previous one uh, which I explained, it is also similar. Here, here it is, here it is like uh, the same thing, same thing. Here it is, here it is. First step is palladium L2 to palladium. So this step is OA. That is, we call this step as a oxidative addition step. So next step is, so again, that the addition of R, addition of R. Okay, so addition of R. So we have, again, this is a one kind of addition step. And this step is that is this step is, that is these two L group, these two turns to each other. Now in this step we are seeing these two L group become cis together. So this is trans and this is cis. So mainly this step is a cis trans rearrangement step. And our, according to the question, our last step is that the formation of R double bond R, that is and then the palladium 2 is going back to palladium 0. So here, this, as we have already said in our last question 1 discussion, that these formation of palladium 2 to palladium 0 is nothing but the reduction, as well as here in this step, here in this step we are eliminating our product. So we are calling the, in this step is the reductive elimination. So our option will be option number D will be our right answer. So here we have already seen that this is a kind of transmetallation step. Is this one is, we can call it the transmetallation step, and oxidative addition step is our first step, is oxidative addition, and cis trans rearrangement is this. So here the four option is there, and our desired one is option, that is path A. That is the step A. Step A is our desired step. So our step A will be the reductive elimination step. So now we got our answer with this catalytic cycle. Here the, as this step is kind of transmetallation step, this step we called this the cis trans rearrangement. I have already explained. So for the question number 4, we have also got our answer, that the so last step is the reductive. So mainly for generally for all catalytic cycle, last step is mainly the reductive elimination state, and for the palladium catalyzed cycle, first step is generally the oxidative addition, and the last step is the reductive elimination. These two are, and in between these two steps the changes can be there. With this I go to the our next question, which is the following reaction is an example of. So as we transfer from Suzuki coupling transfer ourselves to Suzuki coupling, and we have seen that Suzuki coupling is generally represented of R V O H plus R X in presence of palladium PD 0. It is converting to R and BX 2. So this is the general representation of Suzuki coupling reaction. So why this Suzuki coupling? So we got our answer. This is the our one of the coupling partner and another coupling partner. So this is a palladium catalyst and this is reflux. So we got our answer is a Suzuki coupling. But why this problem is interesting over here is the tolerance of two types of functional group which present in our substance. That's why this question is very important. That's why this question is very important here. Why this question is important? That is the tolerance of functional group over the Suzuki coupling, which is another important thing for the Suzuki coupling reaction also. So we have our one coupling partner, that is the our boronic acid, another is the aryl bromide. So here we have two functional group. One is these types of ketone, another is these types of nitro. Here after this everything reaction is happening, oxidation, reduction. So these nothing happens to this functional group, and the reaction and oxidation is happening only on the palladium catalyzed cycle. So that's why this reaction, there is the example of this reaction is very important in the point that this palladium catalyzed Suzuki coupling reaction is very much functional group tolerance, that is it does not affect any of the functional group present in the substrate in most cases. Our next question is in the question number 6 we have then come. So as the Suzuki coupling reaction is undergo by this the BOH whole twice, that is the boronic acid system, so that is mainly the aryl boronate system. So so this reaction is will be only successful reaction when we can mate these types of BOH whole 2 system with more effectively and mm, from other substrate, that is we can convert any functional group substrate to these types of aryl boronic acid substrate. That's why only then we so we have several chemical method which is available by which we can make or convert these our substrate to our desired catalyst substrate through this boronic acid. So next question is quite a little bit example of that thing where we are converting these to our substrate, that is this one. So here we have this cup this reaction to example of this is not a Suzuki coupling, because the Suzuki coupling involves the boronic acid and not a Heck coupling. Heck coupling, we have seen that this is the vinyl halide or any other alkyne also. So our option will be in between two, that is B or D. So our option will be in between the two. So let's talk about the option B, that is the haloboration reaction. So what is haloboration reaction? Let us illustrate the example of haloboration reaction which is already discussed. So let's see one more time the haloboration reaction. So our haloboration reaction is, we have R dash C triple bond CH. When we are reacting this with bromine derivative BBr3 in presence of IPR whole twice O, then we are having this reaction R1 H IPRO whole twice, and here is the Br, that is the addition of haloboration. So addition of this is the boron and halogen and bromine in a alkyne substance. So this is the example of haloboration reaction, that is the addition of halogen as well as bromine to the alkyne substance. So this is a mainly example of this reaction. But our reaction is, what is added? So here in this alkyne substance we are adding a hydrogen and a boron. So simply the example will be hydroboration reaction. This is not a haloboration reaction. So here we have seen that by applying simple knowledge we can get our reaction if we have the brief idea of thing. So brief idea of chemistry. So here, as the hydrogen and bromine is adding to our alkyne, so this is simply a hydroboration reaction, not halo. When this halogen, that is the BBr3, in presence of this reagent is adding to our substrate, that is the addition of halogen as well as this boron, we call it as a haloboration. What is the use of this? When we are having that another, I have already seen that this is R2 ZnX in catalyzed by L2 PD Cl2, it gives R1 R2 twice. So this reaction, this step we called Negishi coupling. Negative coupling reaction. So this is the organo zinc reagent is used with this haloborated product to give the another coupling product to give this. So here in this case our reaction is, according to question, is the hydroboration reaction. So option D will be the correct answer. Coming to this question number 7. So again we are returning to the Heck coupling. So from the Heck coupling reaction we are observing several types of questions. several types of question which is very much important in exam point of view. Also it is very much important for understanding this reaction in proper way. So our question number 7 for the seventh question of the day is the one that represents the Hake coupling is. That is, to answer this question, we only need to know the general expression for Hake coupling reaction. We need to know the general expression for Hake coupling reaction. So in our case, the general representation for Hake coupling is, as we have already seen, that we have so this is our general representation for Hake coupling reaction. It is the palladium 0. So we have so here there is a coupling of these carbon atom is happening with these carbon atom, and here both the carbon is sp2. So here our coupling, Hake coupling is representing the is sp2 coupling. So this question is very much important, whereas we have seen that the Suzuki coupling reaction, whereas mainly the boronic acid, that is the Ar BOH whole thrice whole twice and our Rx. So here mainly our coupling is that one is sp2 and another is the sp3. So the different coupling we are seeing, we are observing in so here, and the coupling partner is also different. So our question is the Hake coupling reaction. We have our coupling partner, that is the sp2, and sp2 coupling is happening in Hake coupling reaction. So we have seen that how different kind of question can be framed from a different only a particular single types of reaction, and how to approach these types of question. I hope with the video session maybe the participant is not there, but with watching the video session in the um, um, in the YouTube, we are having uh, the knowledge more inside the mm, topic with through this question answer solving session. So this question answer solving session, I believe, that will increase the ability to understand more deeply the concept and the different procedure or technique to approach the question in different competitive exam. With this, I come to the eighth question of today, which is the same question from the Suzuki coupling reaction. I have already stated the answer. So our question is the organoboron reagent is used in. So see that in a Suzuki coupling reaction we have answered several types of question from the catalytic cycle, from um, uh, from the catalytic cycle, from their application and their substrate scope, their functional group tolerance, etc. So with this question solving session, I think that this will have an overall and good general idea about the particular coupling reaction. As today we are reading the Suzuki coupling reaction and the Hake coupling reaction mainly, and how different types of question can be formed on a particular types of reaction, coupling reaction. So so here we have seen that we have already discussed the organo how that is the organoboron reagent, how helping to acids the Shishi cross coupling reaction. The main importance is this has become one substrate is nucleophilic in nature, another substrate is electrophilic in nature. So there is no scope for the homocoupled product. That is the beauty of these CC coupling reactions. So we are only having the heterocoupled, that is the CC coupled product. So homocoupled product formation, so in these types of cross coupling reaction is almost zero. That's why we are reading this coupling reaction is more detailed and understanding their concept in more detailed way. Okay, so our is the organoboron reagent is used for the Suzuki coupling reaction. So this will be our correct answer. Okay, so with this I completed the eighth question of today's series. Now I going to the ninth question of today's series. Ninth question is very much an important question, and as we going to the last of our session, we have seen that we have covered different coupling reaction. The Hake coupling reaction we covered and see that catalytic cycle in more detail, and what is the problem with the substrate, what types of particular substrate we can use. We have seen that in oxidative addition step for Hake coupling reaction, that the substrate should not, that is the aryl that is the halide substrate should not contain any beta hydrogen reaction. Otherwise uh, this substrate will undergo the beta hydride elimination reaction in presence of the catalyst, and in oxidative addition step it will not go through the alkene insertion step for this Hake coupling reaction. Also, for the palladium catalyst Suzuki coupling reaction, we have seen that the importance of boronic acid, which will conveniently access through the haloboration or hydroboration reaction of acetylene of different alkyne groups to give them CC cross coupled product with very much um, good yield. So good yield, and the in these times of reaction no homocoupled product is observed, only are having the heterocoupled product. Hmm. Now we go into the another coupling reaction system, which is known as the Stille coupling, which involves the organotin reagent for coupling partner with our halide reactant. So here our reaction is in presence of palladium, same thing, that is in presence of CO is also there. So our question is, what is this? SPSP2. Okay, so here this is nothing. We are having our Stille coupling reaction. So what is happening here? Here our is the palladium, and that is the palladium catalyst in presence of carbon monoxide, THF, and 50 degree centigrade. This is the our substrate, which is characteristic for this Stille coupling reaction. So here we have seen that our organotin reagent NBU3SNR, which is our Stille coupled reagent or substrate. So we need to make this substrate for Stille coupling reaction. So also here is a very important role of CO. CO help is to form the um, if like if we have different kind of this one and another is like this RX. So in presence of CO with this condition palladium catalyzed, this condition will have RCO R dash. This is a very important, so that we need to remember when we are seeing that NBU3. This is the another Stille coupling reaction, and also in presence of CO, it is forming the ketone, not the CC coupling reaction. That is here. We can say that the CO is mainly undergo the insertion types of reaction. Reaction. So here our coupling partner is, here two things is happening. So this is basically a product, that means this is a MSQ type question. So here we need to see what is happening over here is this iodide, and another thing is H. So our these two is our addition types of couple types of reaction. So without show show without CO, we only have our CC coupling reaction here as here H. But in presence of CO, we will have C double bond OH. So here our option will be C as a product in our reaction. But ES become a MSQ type question. So here what will be the other product, that is the what will be the fate of n-butyl SN, n-butyl whole thrice SNH. So n-butyl SNH simply take this iodide to become the n-butyl 3 SN iodide. So our answer will be A, C and D. So answer will be C and D. So here the coupling is also happening in a sp2 carbon center. This is another thing to note down here the Stille coupling is also happening in this reaction in sp2 center is involving over here. So here hydrogen and this will, if this is not, then I have already explained that this without this only hydrogen will be came here, but release of this, but in presence of CO reaction will be something different. It will generate a carbonyl group inserted in between the two reactant. So this is another important question from the Stille coupling reaction. Now this is another important question, as we are reading different types of reaction, so we need to know which metal is catalyzing which reaction. So here our question is the reaction is catalyzed by palladium is. So as still now we have discussed the alkylation, Higgs coupling reaction, Suzuki coupling reaction, Negishi coupling reaction, and the Stille coupling reaction. So all of this reaction is catalyzed by palladium. So here, so we have seen that there are two options which we have already discussed. So with this, we can already tick mark these two options. That is the Suzuki coupling reaction and Higgs coupling reaction. This is also an MSQ type question. So this is also another example of how we can frame a question on single topic. It is a very easy question, I believe, but we have not read that the surface oxidation is another different thing. We will read also the hydroformylation reaction involve the rhodium catalyst. We will see it in upcoming classes. Mm, so here our answer will be B and C, which is catalyzed by the palladium only. Now we have come to the last question of today's discussion session. Now we have came to the last question of today's question answer discussion session, and this question is very much important. I believe this question is very much important in for the Suzuki coupling reaction, and how in uh, recent years people have overcome different problems and how make this more effectively with low catalyst loading, also activating different kind of substrate by mm, different activating different kinds of substrate by modifying the ligand system only. Mm, so this is last question of today's this discussion series. Okay, so with this we came to the last questions of today's discussion series, and that is the correct statement that depicted the ligand influences in Suzuki coupling reaction is. So this is the important reaction, important thing of reaction. So Suzuki reaction, we have seen that we are having uh, um, Labi group, that is the mainly the halogen group in our system. So which first undergo the oxidative addition, but the how the mm, thing is, how the mechanism of the this reactivity of this aryl halide, or the halide thing is mm, overcome by this the reactivity rate of this coupling types of reaction. So we will see with this example of the halide. So Suzuki reaction, we have seen that Suzuki reaction, we have seen that we have our PdL2 L2, which is mainly the palladium in zero oxidation state. So here we are adding our RX. So here X is iodide greater than OTF greater than Br and very greater than Cl. So this order of is explain the reactivity. So with this reactivity order, we have seen that up to bromine this reactivity is very much highest. Obviously for iodide and OTF the reaction is very fast, but their preparation is quite difficult. So but the preparation of bromine is quite easy. Also the chlorination, that is the chloride, is also easy. But for the bromine, we have seen that the reaction is very faster for this oxidative addition reaction step, that is PD, L, L, X and R, that is the palladium in, that is the OA. Now if we have a substituent, that is the RCl, this reaction is having very much low oxidative addition rate. So now to overcome this, we can design a ligand system in such a way that this helps to overcome this rate limiting effect, that is the slow rate of oxidation addition effect. How we can do that? So for that we have designed another ligand system which will solve out our these problems. So for this we have designed aryl so when we are having so that so as I have already said that this coupling reaction is only applicable or largely applicable for the iodide, triplet or bromide, but it are chloride or aryl chloride, because of the strong this carbon halogen bond, so reactivity of this thing is very less. So now we can overcome this reactivity using our designing our different ligand system. So in presence of palladium, so let's take an example and illustrate this. um, okay, let's take an example. So here we have our aromatic, that is R and B OH whole twice, our boronic acid plus our aryl derivative which undergo chloride, mainly the chloride derivative which undergo the coupling reaction. Here we can use the R dash. So here we can here we have the palladium acetate, where here have the palladium acetate as the catalyst, as we have already seen, but we introducing another ligand, that is like looking like this. in presence of in presence of KF 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 and dioxin in 25 degrees centigrade, we are having this coupled product. We are having this coupled product in very much greater than 90% yield. So here this is the main role of this ligand to promote this aryl chloride to give the effective product formation is a more than 90% yield. So here we overcome the less reactivity of uh, aryl halide using this ligand. So how this ligand helping? Here the importance of this bulky. Then going to our question. So here what is that is the electron rich nature of the ligand promotes the reductive elimination step. Electron nature of the ligand promotes the oxidative addition state. Bulky ligand facilitates the oxidative addition and bulky ligand facilitates the reductive elimination. So we have seen that in our this bulky ligand so helps increasing electron density with this donating into the palladium center, which helps the oxidative addition of this aryl halide moiety undergo to more better way of oxidative addition. Also, because of this two tributyl group in this catalytic cycle also helps the reductive elimination process to mm, eliminate this product. So here our two challenge, one is the oxidative addition step, which also overcome by this electron more donating effect of this ligand, which donate more electron to the metal, and this preparation of bulky tributyl group will help to facilitate the reductive elimination step. So with this we can say that so enhance OA, that is this bulky ligand enhance the oxidative addition state, and second enhance R reductive elimination step. So these two ligand is helping the two step, which is most important step of catalytic cycle. So going to these options is so electron rich nature of this ligand promote. So we need to promote the reductive oxidative addition, that is promoted by electron rich nature of this ligand, and the bulky ligand which facilitated the reductive elimination step. Because of the bulkiness, the elimination of the product become facile. This bond become less stable with the metal complex. So our option will be option B and option D will be correct answer. Also it is a MSQ type question. So with this I come to the end of today's discussion series of the questions. So today we have saw different types of question from the mainly the Suzuki coupling, Heck coupling, Negishi coupling reaction, and So today we have seen different types of coupling reaction, that is the Suzuki coupling reaction, Heck coupling reaction. One is the Negishi coupling reaction, and also the Stille coupling reaction, and their importance, how they came to this from laboratory to industrial application, and why the palladium is most important in this reaction step. Also, the Suzuki reaction we have discussed, why the boronic reagent is useful, and here the CC coupling reaction, we have seen that no homocoupled product is observed, only the heterocouple, because of the carbanionic and carbocationic, carbanionic and carbocationic nature of the substance. So there is no scope for the hetero coupling or homocoupling, no scope for homocoupling product formation. Also, the palladium is very much air and moisture stable, and it is way cheaper than their catalyst, and that is the rhodium and iridium, which is best known for the catalyst till date. So also we have seen that the how to overcome the reactivity of the substrate, that is the we can increase the rate of the reaction by only designing the different ligand with the catalytic reaction. So there is a ligand assisted palladium catalyst reaction helps to accelerate the reaction. We have seen the example for the palladium for the palladium for the palladium mm, catalyzed aryl chloride substrate for the Suzuki coupling reaction. So I hope in this session we have covered most of the topic in today's week, and also we discussed the general catalytic cycle, as well as how this catalytic cycle have the different name, and how this name is designing um, or designing each step of the catalysis. Mm. Uh, so I hope this session is helping everyone to solve the assignment problem, as well as it will help for the assignment problem, as well as it will help to it will help to solve questions in the final examination, as well as different competitive exam. Main motive of this session is to interact with the learners, but as no learners present, I have continued this session from my side and discuss several problems which is related to the course, and for better understanding the course. I hope this session will be helpful, and this recorded session is uploading as previous. I am uploading to the YouTube. You can directly go to the session, and if you have any doubt, anything, any question regarding to the course content, you can directly ask in the discussion forum question. We are trying to answer this as early as possible. So with this I want to thank everyone who will join this course, who will join this course, and who will watch this recorded session. I believe this session will help you to understand the course content in more deeper way, and to solve your assignment problem, as well as your different question with this topic in different examination, and the final examination also. Also, I am came to the end of this student session. I will close this session in upcoming 5 minutes. Okay, I think this session will helpful to all of you who will watch this session. I request everyone to join this live session so that your doubt get cleared in live session, and I will try to clear your doubt. In between, if you have any doubt, you can post your question in the discussion forum. We will try to answer those questions as quickly as possible. So with this, I thank you everyone and for watching this session, and bye for this, and I'll see you in the next session. Okay.